welcome. Thank you all for coming. I'm Johanne, and for those of you who might not know me, I'm doing my PhD very, very soon, not anymore, on inner speech and how we talk to ourselves when we try to get through something that's a bit boring or difficult. And this seed funding project kind of ties into that. But I've worked on it with Mikkel and Line, and it kind of ties into both of our PhD projects, mine and Line's. It came from discussions on like the role of inner speech in both motivation, but also when inner speech kind of gets out of control, and it can be involved in things like anxiety and depression. When it's like the rumination, for example, you're familiar with that, like repetitive negative self-talk. So we thought, could there be a way of measuring these physiological effects of inner speech? And there are many ways you could imagine doing that. You could measure cortisol, you could measure skin conductance, but we chose to focus on heart rate. So before we get into the actual project, a quick advertisement. We have an inner speech workshop planned on the 25th of May with a star lineup and some random people, which will be very exciting, I think.
I'm the random person.
Me too. So we'll send out invitations for that soon, and it will be in Heimdal, which is also very exciting. So, our research question was, does emotional self-talk cause increased heart rate? Basically, very simply, that's what we wanted to check. And inside this questionnaire, of course, many more. Like, can we even measure the effects of inner speech? Is there a difference between positive self-talk and negative self-talk? So if you're telling yourself like, you suck, you can never do anything right, or if you're like trying to encourage yourself, you can do it. All that stuff. And if there are sort of heart rate effects of self-talk, are they independent from other movement effects? So you can imagine like clenching everything when you're disparaging yourself, or maybe like bouncing your foot or something. So that's why we wanted to set up a project that both measured movement and heart rate. So we did it in the motion tracking lab upstairs. But first, some small bits about the theoretical sort of background for why you would think that inner speech has any kind of effects. So first of all, there's of course positive effects. So there's some studies that have shown that inner speech can help focus attention. So in sports, for example, if you need to angle your catcher racket in a specific way, or focus on where you put your feet or how you hold your back when you're running, inner speech can focus attention on these specific things. It can also maybe distract from pain and discomfort. So there are some studies with people cycling in uncomfortable heat, and if they are trained to talk to themselves in specific ways, they feel the heat less, or they feel the discomfort less. So it's mainly through, inner speech looks like it has effects mainly through reducing the perceived exertion. So like how you're constantly monitoring yourself and trying to figure out how long you can keep going, and that threshold sort of changes. It's the same idea with inner speech and motivation. Yes. So I often think like how exactly does this work? How can talking to yourself in a specific way actually change what your body can do? Which is very mysterious, I think, but you can build off an intuition by thinking about what happens when other people talk to you. So if your coach or something says, come on, you can do it, then you can actually do more than if they haven't said anything to you. So in this specific seed funding project, we wanted to look at negative self-talk mostly. And this is of course tied to anxiety and depression. I'll give you a few seconds to read this cartoon. This kind of self-talk is related to catastrophizing, so you think about everything that could go wrong in a social interaction, for example, or you're like perpetuating your negative self-image. You're thinking like, oh, everyone hates me, why can't I do anything right? And you might also go over old conversations and future conversations and think, everything went wrong. And ultimately, this kind of stress over time can lead to some heart-related issues, like high blood pressure, etc. So that's also part of the reason why we wanted to look at heart rate. We wanted to try to induce this kind of self-talk in poor, unsuspecting volunteers. Yes. And then measure their heart rate. So we had two wonderful research assistants, David and Anya. Here is Anya demonstrating the setup. We had 8 motion tracking sensors on each participant, kind of chin and cheeks, and then on each middle finger, on each toe, and on the chest or stomach. And that could sort of measure respiration, the movement going up and down. It's actually fine-grained enough for that. So in the motion tracking lab, for those of you that haven't been there, there's like 9 cameras or something all around, and they record the sensors, these little gray balls, and then they record how they move around in 3-dimensional space. So we did that because we wanted to check that the heart rate effects we might see were not just due to them moving around. Yes. So the motion tracking measured each sensor at a rate of 100 hertz, 100 times a second. And then this chest and stomach sensor measured respiration. And we could measure how they moved on like 3 axis. And then our heart rate measured at 1,000 hertz, which might be a bit overkill. But this is an example of ECG, actually our nose. So we measured the motion and the heart rate across 3 different conditions. Neutral self-talk, where they were just counting. Positive self-talk, where they were encouraging themselves and telling themselves how great they were. And negative self-talk, where they were being very mean to themselves. We switched between a kind of emotional trial, they were 3 minutes long, and a neutral trial. And then they rested for 10 minutes in the beginning so we could get their heart rate down to start with. Based on piloting, we found out that it's not very comfortable to end on a negative self-talk trial. So if the conditions were randomized in such a way that they got a small positive trial to end on. And then we also asked them afterwards how they were feeling and all that stuff. Yeah, and most of the participants actually enjoyed this very much. Like the whole experiment. Yeah. We also asked them to rate how they were generally feeling. This is a 9-item, very short, depression questionnaire. Turns out that they were kind of normal in their distribution with depression, which means that a third of them had moderate depression. Apparently, Lita told me that that's normal.
That's what's seen in the general population.
Yeah. Yes, and then we asked them about rumination, because we thought the inner speech stuff would be related to rumination. We have these repetitive negative self-statements. And we also asked them how often they generally experience talking to themselves, and which condition they found most difficult at the end. most of them found the counting condition easiest. Yeah, it's nice in a way that they didn't find the negative condition easiest. Right. So we pre-registered our hypotheses. This is data from one pilot participant. Averaged over 3 sessions with neutral and negative self-talk. And you can see that the neutral conditions indeed have lower heart rate than the negative self-talk. So this was very encouraging, we thought. Wow, what a clear effect. This is going to be great.
Was the participant naive?
Yes. And this is sort of what we thought we might see, with neutral having the lowest heart rate, followed by positive self-talk, and then followed by negative self-talk. Yes, we had our 2 hypotheses. Emotional self-talk, higher heart rate than neutral, negative higher heart rate than positive. And then we decided to exclude a trial if motion on one of the sensors exceeded 3 standard deviations. So if they were basically bobbling their foot a lot. Yeah, or something like that. Yes, we thought we had a very simple idea. It was not. Here's data from one sample participant resting first. So we can see that the 10 minutes were actually necessary to kind of get them down. Well, it keeps going down, but at least to get them on some kind of resting heart rate area. The first negative trial, the green one, very clearly a spike there, but then kind of the effect is a bit less strong data on. Yes, we resampled the heart rate to 1 hertz. But it's good that we had such fine-grained data in the beginning, so we could calculate heart rate from the ECG. And quite precise. And here we have everyone, all the participants. And as you can see, there are some participants who have very strange data. And this is a recurrent theme in this seed funding project, that it was very difficult to kind of juggle the motion tracking data and the heart rate data and everything, and the poor Kobe laptop that we used to collect all this data was very tired sometimes of running all these heavy programs all at once. But for most of them, we got some very useful data. Here again. Everyone, the 180-second trial, not divided into conditions in this case. So we pre-registered that we would take the median heart rate per trial and then use that as the dependent variable, and also delay it for 5 seconds to allow the effect to kick in. Yeah. And as we saw in the other plot as well, there was a quite strong effect of time. So as they were lying down for a very long time, their heart rate got lower. So we also had to model that. Very important. And now I think it's Mikkel's turn to take over.
So that was the positive talk. So now I'm here to lead you into the darkness. So the idea was that it would be easy, as you saw those huge effects that we could get on ourselves in pilot work. We were expecting to see that in our samples as well. You can already see here that there's a lot of noise in these data. The dots here are the median heart rate for a particular trial for a particular participant. Yes, and just to note the plot before, we had 67 participants, and we have pre-registered that we would exclude participants that had motion that would exceed 3 standard deviations from the sample distribution on any sensor. That's simply because we didn't know what to do else. how do you measure non-movement? And because we didn't have a large sample to base our exclusion criteria on, that was our idea. And that we would also exclude participants that then did not have all three conditions. So if we had excluded 2 negative self-talk trials, then we would throw out the participant. So this is important because we started with 67 participants, and now we are going to go a bit lower than that. Also because has anybody here worked with the motion tracking equipment? No. Yeah, I think we were among the first at least to try it, and as Johanne pointed to, there were some issues that we had to deal with. So this equipment crashed on a number of occasions, which also means that we were forced to throw out data on that count. That was my watch telling me that my phone is ringing. Okay, so this is just, so now again showing you how data like this could look. This is one sensor from the belly of one participant, and at some point we have to decide at what temporal resolution we want to analyze these data. And you could say that heart rate is sort of meaningless below 1 hertz, because most people have around 60 beat per minute heart rate. Therefore, we decided to go for 1 hertz, where the 1 hertz is a meaningful movement. Sample rate is another issue, but nevertheless, for the time being, we've downsampled all the movement to 1 hertz as well. So this is an example movement from the belly of one participant, and as you can see, this consists actually of 2 measurement files that we have to merge because we couldn't make the Qualisys equipment run for a whole trial. It would crash. So that's, but there's lots of issues also with then trying to get all of these different files into the same time frame that we've been struggling a little bit with. And 1 hertz sampling rate helps a little bit. If you don't care about the very, very nitty-gritty temporal details, then this problem becomes easier. But prior to even looking at the motion data, we're down to 51 participants. Says something about the level of problem that we were facing with this. Yes. I'm hesitating a little bit there. We should have had a slide, perhaps, with how this motion is actually this signal is generated, because the actual motion signal is not a motion signal but a position signal. And is that have we dropped that slide? Perhaps we have. But the idea is that we have for each sensor we have x, y, and z coordinates, and in order to turn that position signal into motion, we subtract the positions at a time lag of 1, and then we use Pythagoras in order to get a length of movement between time points, and that's what I've plotted here. I hope that made sense. It would have if we hadn't thrown out that slide. But we have time is running, so here are then the distributions of motion a summated motion across each trial per participant. And yeah, so, and they're also scaled, so the length of this movement is sort of meaningless. But the idea is that it's movement regardless of whether the arm is going up or down, or whether the belly is moving up or down, it's counted as positive movement. And then we're summing it and getting something that looks like this. And obviously it's not normally distributed. Most people are not moving a lot. Nevertheless, we had decided on using the 3 standard deviations, so we stuck with that. So all of the trials that are beyond the lines here, we throw out. And if, as I said, if one person happens to have 2 trials thrown out from the same condition, then we throw the participant out as well. That brings us down to 48 participants. And here we now have the results of our pre-registered hypothesis. So we have heart rate as a function of whether a condition is emotional or not. And then we have a condition that says something about the difference between the negative and the positive. Then we have trial number as a covariate, and participant as a random effect. And yeah, so that's the pre-registered model. And as you can see, we have a significant effect of whether you're talking to yourself in an emotional tone or not. So it increases heart rate with more or less 1 beat per minute. Whereas there's no difference between positive and negative. Yes. When I was running this analysis, I thought to myself, why didn't I include trial number, or why didn't we include trial number as a random slope? So now we have that same model, and it increases the effect, but doesn't give us any effect of the difference between negative and positive. So, the conclusion so far is that based on our pre-registered methods, we find a support for hypothesis 1, namely that emotional inner speech is accompanied by increased heart rate. We do not find support for hypothesis 2, namely that there should be a difference between negative and positive inner speech. But wouldn't it be nice to have a plot of these effects so that we can see what actually happens? So Johanne made this plot at some point early in the process. So this is still with 69 participants, and here we have trial time from 0 to 3 minutes on the x-axis, and scaled heart rate on the y-axis. And you can see that the positive and negative here are higher than the control task, but do you see anything else? Any suggestions for what could be puzzling in this plot?
There's convergence in time.
There's convergence in time, so it could be that we should actually have shorter trials, because it seems to be the case that this effect is there primarily in the beginning of the trial. So that's definitely something to consider for future experiments. Do you see other things? Anna?
Maybe prior knowledge, it starts perhaps before the trial, the P.
Yeah, the idea is that this is a downwards going slope, right? From time point 0. That heart rate is actually decreasing, which is a bit strange, right? If you're thinking that here they're starting to talk to themselves in a emotionally charged way, and therefore that should be the point where heart rate starts to increase. So that's not very nice. Yeah. So then we went and made this plot where we sort of expanded time before and after the trial. So this is a little bit misleading. We included 20 seconds prior and after each trial, but there were actually only a 10-second break in between most trials. So therefore, this time period is to some extent overlapping with this time period. But now, what do you see? Yes?
Apparently people got excited that the next trial's coming.
It seems that the heart rate increase starts somewhere around 20 seconds before the onset of the trial. Actually, the increase seems to start already at the end of the previous trial, which is very, very strange. So obviously, once you've seen this, all the rest sort of falls apart until we've tried to explain this. Okay, but important to notice, of course, that this is R's ggplot's smooth approximation of the signal, and this is based on a lot of noise. But if we do a similar plot for foot movement, for example, what do you see? Now a pattern seems to emerge. But again, it's very, very, very strange that participants, for some reason, sense that now the trial is soon over and they sort of get ahead of themselves and perhaps start moving a little bit prior to the trial. But also, if you look at this effect, where there's a smaller effect of the control task, there actually seems to be a larger movement in the control task. I haven't done any statistics on this, so this is just eyeballing it. But at least it seems that although we might be able to explain some of this with this, then there's something about the ordering of these that may or may not be meaningful.
Shouldn't you compare the end of this trial to the end of
So this is the end of the trial, but it's also the beginning of the next trial.
Okay, but it's just in the
So there's
also have the red one, the control.
Yes.
Higher.
Yeah, there's something about the ends of these when you using. So in the best of worlds, these lines would end the same place as this starts, because the beginning and the end is the same. But for some reason, some of these trials are the end trials, and some of them are the beginning trials, and that might. But I guess you're right to some extent. But that's another puzzling thing with this. This is one of the reasons that I'm saying that this is misleading a little bit. Yep. Well, anyway, we had to do something. Again, foot movement. Also, there's a lot of noise in this, so these effects may or may not be built on patterns that are there in all of the participants. So I started filtering the data now to see if I could remove these effects and see what would be left in doing so. And this is not. This is something that requires a little bit of thinking. Something that I'm not good at. But at least I could figure out how to high-pass filter the data, so that the first thing I did in order to get the motion, which sort of has a zero baseline and then moves up and down from that, to try to get something that could be in the same, in a comparable dimensionality. Then I used my knowledge from analyzing fMRI experiments, where we sometimes use something called a finite impulse response set, which is basically just a matrix of zeros and ones, where you shift the one position down through some time period that you want to use, and that gives you, in this case, I used 30 of those, so that I could have, so I had a matrix with time-shifted ones and zeros for 30 seconds each of them. Then, using this and the motion tracking data, so this is an excerpt from one tracker, convolving it with this one, it gave us 30 variables where we had the motion data with a temporal delay of 1 second each. And then we could use all these 30 models here. So instead of just being across 200 seconds, we had it throughout the whole experiment to try to model the heart rate data for this participant. So imagine that this is the whole experiment, and this is the heart rate for this particular participant. Even though the motion here might not be exactly overlapping with the heart rate increase here, if we've time shifted it according to what seems to be the case, namely that is somewhere between 10 and 20 seconds after the fact, then we should be able to use this to regress out some of these effects. Hope this makes sense. At least that's what I did. And I ran this type of regression for all the 8 markers for all the participants, and using them coming up with the residuals. So here we have the high pass filtered data again for this participant that we saw before, and here we now have the high pass and FIR filtered data set from the same participant. And well, I can see a few places where there might have been a filtering effect, but it's not sort of something that jumps out of the data. If we make the same plot as before, this is the plot that Johanne made, but now just with our 48 participants, and then do the same with only the high pass filtered data, and the high pass filtered and FIR filtered data. They might be a little bit different, but then again, might not be. What we then did was to make a new analysis on the filtered data. So here this was just something that I literally just did yesterday evening. So instead of using exactly the same model, I just used trial type here and a median for each participant, heart rate for all the data points of a particular trial type, and then having the control as the baseline here, and then comparing the negative and the positive to the control baseline. And as you can see, both effects are still there. So here's a plot of that. Of course, the variability here is a little bit misleading because these are within participant effects, so we're actually comparing the subtraction of these effects. Yes?
Why is trial type not within the varying random structure? Since it's within participants' effects.
Just want to
No, so now this this is the simplest model you can imagine. So
but you have trial type where each participant undergoes the 3 kinds of trials, right?
yes,
So that could also be possible. So each participant could have different effects from the population.
Yes, so in a sense, because these are set-scored, some of that is already removed, so it's not a big deal, I guess. Yeah. But you could do all sorts of different models here. Of course, I should have done the actual pre-registered model. I just didn't have time for it because the version of this data looks quite a bit different from the one that we did the other analysis on. So, but it will emerge at some point. It was just to have an effect to see whether our filtering did anything. But the point is, I guess, that the strange effect is still there after the filtering. So in a sense, it's a good thing that we still have results, but it's a bad thing that we were not able to remove the obvious artifacts that may or may not be there. Then, looking into the literature, this becomes even worse. I was trying to find a theoretical transfer function between movement of the limbs, for example, and heart rate. And very few people seem to have worked on this, apart from sleep researchers. And a lot of people back in the 60s and 70s were looking at that. And when I then tried to find papers that had looked into this, I found both a paper that said that you could see heart rate preceding movement. So you can imagine lying on your bed and you're a bit uncomfortable, and that might get your back hurts, and that might get your heart rate going, and then you move. Or you can imagine moving, and it's the motion that causes your heart rate to increase. So the idea being that the relationship between cause and effect here turns out to be completely obscure. Of course, this points to a problem in our experiment, namely that we should have randomized our trials even more, and that we should also have had a variable break in between our trials that would have potentially made it possible to model some of these effects. But that is for the future. Now all we can say is that we still replicate the effect after filtering, so all our post-hoc analysis here at least didn't remove the effect. The plot still looks fishy. Cause and effect may not be linear. So there's a lot to work on here. This has turned out to be a very complex phenomenon that we're looking into, but also really interesting. So we're hoping to do more studies on this. I guess that's it.